Not yet. I normally like to give at least 2 minutes for everyone to show up, and not everyone has shown up yet.
Okay, thank you.
All right, good morning, everyone. So today we're going to have a series of presentations that are focused on the topic of antiparasitic and antibacterial metal complexes. And so I believe it's Daniela who will be starting off these series of presentations. So she's already sharing her screen, so I'm going to go ahead and let her start.
Hola, buenas tardes. ¿Me pueden escuchar?
Sí.
Yes, we can.
Ok, pues muy buenas tardes. Mi nombre es Christopher Nieves y junto a mis compañeros en el día de hoy les vamos a estar mostrando una vista panorámica de la aplicación de los complejos metálicos como agentes antiparasíticos y antibacteriales. Pueden darle. A modo de introducción, un agente antimicrobiano se denomina como aquella especie química que es capaz de eliminar o inhibir el crecimiento de los microorganismos. Básicamente, estos compuestos se clasifican según el tipo de organismo contra el cual ellos actúan. Por ejemplo, los antibióticos son agentes antimicrobianos que se utilizan para infecciones bacterianas, los antifúngicos para infecciones de hongos, antivirales para infecciones por partículas virales. En este caso yo me voy a enfocar en lo que serían los antibióticos y es importante recalcar que su clasificación depende mayormente de su propiedad farmacodinámica, su composición química y el mecanismo de acción. Como se ve en la imagen a la derecha, básicamente existen 3 tipos principales o clasificaciones de antibióticos y estas se basan en los procesos biológicos que estos afectan o inhiben, como sería la síntesis de la pared celular, ácidos nucleicos o las proteínas. Pues dale, perfecto. Ok, so a partir del descubrimiento del primer agente antibiótico, alrededor del 1928, el cual fue la penicilina, pues se ha descrito un uso indebido, o sea, se ha abusado del uso de los antibióticos y esto ha resultado en la formación o en la aparición del problema de la resistencia antimicrobiana, que básicamente se caracteriza por el surgimiento de variaciones de microorganismos que son capaces de desarrollar mecanismos de evasión para contrarrestar los efectos farmacéuticos de estas drogas. Como se puede ver en la figura a la derecha, se estima que si este problema de resistencia no se trabaja adecuadamente, para el año 2050 se estiman aproximadamente 10 millones de muertes por año, lo que conllevaría un impacto económico de 100 trillones de dólares. Por lo tanto, es importante para la comunidad científica en este momento desarrollar nuevas técnicas y nuevas drogas capaces de ser efectivas contra las bacterias patogénicas que son resistentes a los agentes antimicrobianos que se conocen hoy día. Si evaluamos históricamente la composición de los diferentes agentes antimicrobianos, vamos a encontrar que la gran mayoría de ellos se componen de moléculas orgánicas, pero sin embargo, en las pasadas décadas, los compuestos de coordinación que contienen metales de transición han llamado la atención de los diferentes investigadores en el campo de la química medicinal, debido a que se han encontrado diferentes complejos con propiedades biológicas que incluyen su uso para el tratamiento del cáncer, malaria y otras enfermedades neurodegenerativas. En este caso les quise traer el ejemplo de Salvarsan, que fue básicamente el primer complejo a base de arsénico que se identificó como efectivo para lo que sería la enfermedad del sífilis, que es una enfermedad de carácter microbiano. Y cabe resaltar que a pesar de todas estas propiedades biológicas reportadas actualmente para estos compuestos, bien poca atención se ha prestado a lo que sería la aplicación de estos compuestos como agentes microbianos, y por lo tanto, en estos recientes años, pues la comunidad científica se ha enfocado entonces, basados en las diferentes propiedades farmacodinámicas de estos compuestos, en analizar su posible aplicación como agentes antimicrobianos. Puedes pasarla.
Ok, pues saludos, soy Daniela, y junto a mi compañero Christopher escogimos este artículo que trata sobre la síntesis y caracterización de complejos de níquel y cobre con ligandos tridentados de tiosemicarbazonas. Entonces, en este artículo se enfocan en su caracterización y síntesis, como mencioné, pero también en su interacción con el ADN y la actividad antibacterial.
Daniela, before you continue, two things. Can you hide that meet.google.com, please?
Yes. Okay.
Thank you. And one other thing, I will let you know when you have 2 minutes remaining. Okay, thank you.
Thank you. Ok, pues el ligando utilizado en este artículo es una tiosemicarbazonas que la podemos ver en esta estructura. Es un ligando orgánico multidentado con actividad antibacterial, antiparasítica, antifúngica y antiviral. Entonces también se ha estudiado extensivamente como agente anticancerígeno, ya que se ve que tiene una capacidad para interactuar con el ADN. Un ejemplo es la triapina, que es un inhibidor potente de la enzima ribonucleótido reductasa, que es importante para la síntesis del ADN, y entonces en este proceso se forman especies reactivas de oxígeno. En este artículo de Sheva del 2019 se ve que la triapina enlaza al hierro 3, reduciéndolo a hierro 2, lo que lleva a una formación de especies reactivas de oxígeno, y entonces también inhibe una tirosil importante en el sitio activo de las enzimas, y por eso es que la puede inhibir. Ay, no me está pasando el slide.
Try escaping and then going back into your presentation.
Okay.
Don't stress. It happens to me.
Ay.
If it continues, I can present for you, okay?
A ver, ay, tampoco. Ah, sí, ahora sí, con la flecha me dejo. Ok, entonces, el método de enlazamiento de las tiosemicarbazonas se conoce como un sistema NNS donante porque el metal se enlaza a la azometina, que sería esto que estoy señalando aquí, a través de los dos nitrógenos, y también se enlaza a la tioamida, que es esto que estoy señalando aquí, a través del azufre. Se ha mostrado que la actividad citotóxica de estos ligandos se mejora con la coordinación al metal, específicamente cobre, níquel, zinc y paladio. Entonces, la formación del complejo metálico mejora la lipofilicidad y el mecanismo de acción del complejo en la célula. Y se ha reportado que tiene una actividad antibacterial. Los objetivos de este artículo fueron sintetizar y caracterizar complejos de tiosemicarbazonas con cobre y níquel derivados de 2-acetilpiracina y probar su potencial antimicrobial en contra de bacterias gram positivas y gram negativas. Y además adquirir conocimiento sobre sus interacciones con el ADN a través de técnicas como la espectrometría ultravioleta visible, electroforesis de gel y medidas de viscosidad. Entonces aquí tenemos el ligando, que básicamente eran dos ligandos que solamente se diferenciaban por este grupo R, que en el ligando 1 era un hidrógeno y en el ligando 2 era un cloro, y eso lo hicieron para ver si la electronegatividad de este sustituyente afectaba a su actividad.
Como los estaba describiendo mi compañera, el trabajo de estos científicos comenzó con la síntesis de los ligandos y los respectivos compuestos de coordinación de ellos. Básicamente, como se observa en el esquema número 1, la síntesis de los ligandos de tiosemicarbazona se llevó a cabo en un proceso en una ruta sintética de 3 pasos, comenzando con derivados de anilina. El primer paso constituye una adición nucleofílica al disulfuro de carbono, seguido por una sustitución con la hidracina. Finalmente, una condensación con la 2-acetilpiracina resultó en lo que sería la obtención de la tiosemicarbazona a base de 2-acetilpiracina. Luego de obtener estos ligandos, pues estos investigadores procedieron a sintetizar los compuestos de coordinación correspondientes, y para esto simplemente se trataron los ligandos con las sales de nitrato hidratadas de cada uno de los metales correspondientes, que en este caso son cobre más 2 y níquel más 2, en soluciones alcohólicas. Como se ve en el esquema 2, en este caso los complejos que se identificaron como complejo 1 y complejo 2 son los que contienen a cobre más 2 como el centro metálico, y el complejo 3 y 4 corresponden a los complejos que tienen a níquel más 2. Una vez se obtuvieron todos estos compuestos, procedieron a caracterizarlo utilizando diferentes técnicas espectroscópicas, gravimétricas y analíticas, las cuales incluyeron lo que es la espectroscopía de NMR, la espectrometría de masa, cristalografía de rayos X, determinación del punto de fusión, análisis elemental, absorción atómica, espectroscopía de infrarrojo, etc. Finalmente, para poder entonces evaluar la actividad biológica de estos compuestos, ellos se enfocaron en lo que sería la interacción de estos complejos con el ADN, y para esto utilizaron 3 técnicas básicas que incluyen lo que sería la medición de la viscosidad, electroforesis de gel de agarosa y experimentos de absorción electrónica. Mediante estos experimentos ellos pudieron entonces obtener información acerca de la naturaleza de las interacciones de estos compuestos con el ADN y detectar si hubieron alteraciones en esta molécula, incluyendo lo que serían los rompimientos oxidativos de la molécula, y evaluaron la actividad antibacterial en contra de bacterias gram positivo y gram negativo utilizando el método de microdilución. Como se puede observar en esta diapositiva, uno de los primeros experimentos que estos investigadores realizaron para caracterizar los ligandos fue espectroscopía de NMR. En la figura número 1 se representa lo que sería el espectro correspondiente al ligando número 1, en este caso es el espectro de protón. Estos investigadores también realizaron espectros de carbono y otros experimentos en 2 dimensiones para caracterizar los compuestos, y en estos casos se observaron las bandas características correspondientes a estos compuestos. Luego de realizar estos experimentos con la espectroscopía de NMR, estos investigadores procedieron a determinar la estructura cristalina de estos ligandos utilizando la cristalografía de rayos X. En este caso, como se observa en la figura 2, tenemos un esquema de lo que sería la estructura química de los ligandos, y si observamos en la tabla número 2, ellos pudieron confirmar la formación de la imina gracias a la evaluación del enlace entre N12-7, que corresponde entonces a los átomos que están involucrados en ese enlace imina, y ellos encontraron que el largo de enlace corresponde al largo de enlace típico doble entre carbono y nitrógeno, lo que confirma la formación de ese grupo funcional. En adición a esto, ellos lograron describir un proceso de tautomerización, que en este caso esta molécula es capaz de existir en un equilibrio dinámico, y en su estado sólido ellos indican que predomina lo que sería el tautómero tiona. Esto fue confirmado mediante la evaluación de los diferentes largos de enlace entre el carbono de azufre y nitrógeno-nitrógeno. Básicamente ellos encontraron que estos enlaces, específicamente el de carbono y azufre, es más largo que un enlace típico doble entre estos 2 átomos, pero es más corto que un enlace típico sencillo entre ellos, lo que indica entonces que existe en realidad un equilibrio entre ambas estructuras. Pero sin embargo, ellos indican que el tautómero tiona es el que prevalece en el estado sólido. En adición a esto, utilizando la cristalografía de rayos X, ellos pudieron determinar que el ligando número 1 cristaliza en lo que sería una celda unitaria triclínica, habiendo 2 moléculas de ligando por cada celda unitaria. En adición a esto, utilizando los diferentes ángulos de enlace que se observaron para entre los átomos de carbono y nitrógeno, ellos pudieron determinar que la estructura principal de este compuesto adquiere una conformación plana, y esto se debe a que están en el rango de 103 a 127 grados, lo que indica un carácter sp2 para todos estos átomos. Otra de las propiedades físicas que ellos determinaron para caracterizar sus compuestos fue la determinación del punto de fusión. En este caso, como se observa en la tabla número 3, todos los compuestos tuvieron puntos de fusión mayor a 200 grados Celsius. Y en las columnas adyacentes se encuentra el análisis elemental, donde se determinó la composición porcentual de cada uno de los elementos, incluyendo los metales que componen al ligando. Y pues en este caso ellos observaron que el valor experimental, que vendría siendo el que está en la izquierda, se acerca o se aproxima bastante bien a lo que sería el valor teórico, que es el que está representado en la derecha. Para poder confirmar lo que sería la estequiometría entre el metal y el ligando de estos complejos, ellos utilizaron el método de variación continua, o mejor conocido como el método de Hopf. En este caso, ellos pudieron determinar que la estequiometría entre el metal y el ligando es de 1 a 1. Utilizando la espectroscopía de infrarrojo, ellos pudieron ganar más información acerca de cómo es la estructura de estos complejos. Por ejemplo, ellos pudieron determinar que el ligando actúa como un agente quelante neutral, o sea, su tautómero tiona, y esto se confirmó debido a que no se pudo observar la banda característica del grupo tiol, que salen aproximadamente de 2600 a 2800 centímetros de menos 1. Ellos pudieron confirmar la coordinación de los metales a través del grupo azometino, y esto fue gracias a que se observó un desplazamiento leve en lo que sería la banda de vibración a números de ondas menores comparados con los ligandos solos. Y finalmente ellos también pudieron confirmar que el ion nitrato ocupaba el cuarto lugar de coordinación de este metal, analizando 3 bandas características de los modos de vibración de este anión, lo que, como les mencioné, confirma que el anión entonces está participando en la coordinación del complejo. Finalmente, ellos realizaron unos análisis termogravimétricos para analizar lo que sería la estabilidad termal de estos compuestos y la posible presencia de moléculas de disolvente como agua o metanol en la red cristalina de los complejos. Y en este caso, para los complejos del 1 al 3, ellos determinaron que el proceso de descomposición ocurre en 2 pasos, y pudieron identificar los productos que se forman, que en este caso son los nitratos correspondientes a estos metales. Y en el caso del complejo número 4, observaron que solamente ocurre un proceso de descomposición que resulta entonces en la formación de un solo producto. Es importante recalcar en este caso que ellos determinaron que los compuestos de níquel son más estables termalmente que los de cobre, porque se descomponen a una temperatura mayor, en un rango de 250 a 500 versus 50 a 270, que corresponde para los de cobre.
Ok, en los próximos set de experimentos fueron para evaluar la interacción de los complejos con el ADN. Para repasar unos conceptos, hay varias maneras en que los complejos pueden interactuar con el ADN, pero 2 de ellas son el enlazamiento intercalativo, en donde el complejo se interpone entre las parejas de bases, o el enlazamiento con los surcos, que sería el enlazamiento a los surcos mayores o menores del ADN. Entonces, esto es importante porque, por lo menos para lo que es el enlazamiento intercalativo, esto puede verse experimentalmente mirando el espectro de absorción, porque cuando ocurre la intercalación, ocurre un desplazamiento del largo de onda máximo, que puede ser a largos de ondas mayores, conociéndose como un desplazamiento batocrómico, o a largos de ondas menores, que es un desplazamiento ipsocrómico. Entonces, esto ocurre porque la intercalación lo que hace es que cambia la conformación del ADN, de forma de que ya recibe una cantidad distinta de radiación. Entonces, para los ligandos 1 y 2, no vieron ningún cambio significativo en el espectro de absorción, lo que indica que la interacción que estaba teniendo con el ADN era con los surcos. Mientras que para los complejos 1 al 4 se vio un desplazamiento ipsocrómico gradual al aumentar la concentración del ADN del timo del ternero, que fue el utilizado en este experimento, lo que indica que hubo intercalación. Aquí podemos ver los espectros. A la izquierda tenemos el espectro del ligando y podemos ver que al aumentar la concentración del ADN se mantiene constante la banda y el largo de onda máximo no se desplaza. pero a la derecha tenemos el complejo número 1, que sí se ve un desplazamiento a largo de ondas menores al aumentar la concentración del ADN. Entonces, la coordinación del metal facilita la intercalación porque dos cosas. Primero, hace que el complejo sea plano. Si vemos al ligando por sí solo, vemos que puede haber rotación en estos enlaces de los nitrógenos. Entonces, pues, cuando se enlaza el metal, básicamente está fijando la molécula a través de los nitrógenos de la sometina y el azufre de la tiamida, y está básicamente obligándola a quedarse quieta y fija, y no va a poder rotar, lo que facilita que pueda interponerse entre las parejas de base en el método intercalativo. Además, ellos mencionan, el artículo menciona, que estos anillos aromáticos de la molécula pueden interactuar con las bases nitrogenadas del ADN. Otro experimento que hicieron para evaluar estas interacciones con el ADN fueron medidas de viscosidad, ya que estas medidas sirven para identificar alteraciones estructurales en el ADN causadas por las interacciones con los complejos metálicos. Cuando hay intercalación, esto provoca que el ADN se desenrolle. Entonces, si se desenrolla, se alarga. Y cuando tienes una molécula más larga, su viscosidad va a ser mayor. Si la interacción es a través de la interacción con los surcos, no se ve este desenrollamiento del ADN, no se alarga tanto, entonces el aumento en viscosidad no se va a notar tanto. Entonces aquí tenemos una gráfica de la viscosidad al aumentar las concentraciones de los ligandos solitos, que son las líneas verdes y vino, o al aumentar la concentración de los complejos, que son las líneas rojas. A la izquierda tenemos los complejos 1 y 2 y a la derecha tenemos los complejos 3 y 4. Y podemos ver que al aumentar la concentración de los ligandos, la viscosidad se mantiene constante. Pero cuando aumentas la concentración de los complejos, la viscosidad disminuye. Entonces, yo dije en el slide anterior que si el método es intercalativo, uno esperaría un aumento en viscosidad. Pero aquí estamos viendo una disminución. Entonces, esto lo que indica es que el método intercalativo en este caso es parcial. Y como es parcial, esto causa unas torceduras en el ADN que en vez de alargar la cadena, lo que hace es acortarla. Y al acortarla se disminuye la viscosidad. Ok, entonces en el próximo experimento, que es a través de la electroforesis de gel de agarosa, esto se utilizó para ver los posibles cambios en la conformación del ADN o cortes en el ADN que pueden provocar los complejos. Y esto es importante porque cuando cortas el ADN o lo alteras, esto puede conducir a una apoptosis, lo que puede tener una aplicación antibacterial. Entonces, para explicar esto, hay tres conformaciones que son la forma 1, que sería el ADN superenrollado. Y si cortas este ADN superenrollado, quedas con la forma 2, que sería esta forma circular relajada. Y si lo vuelves a cortar, vas a quedar con esta forma lineal. Entonces, las movilidades de estas tres formas es distinta y por eso podemos usar esta técnica para ver si hubo un corte en el ADN. Entonces, en la forma 1 tiene una movilidad mayor, por eso vamos a ver que está más desplazada la banda, y la forma 2 tiene una movilidad menor. Mencioné que la forma 1 era el ADN superenrollado, entonces para ver si se cortó el ADN, tenemos que ver la aparición de la banda en la forma 2, que sería esta. Aquí esta imagen no se ve muy claramente, pero voy a explicar lo que se supone que viéramos según las conclusiones del autor. Aquí tenemos las bandas de los complejos 1, aquí los de los complejos 2. En la primera tenemos el complejo solamente, y del 5 al 7 tenemos distintas concentraciones del complejo, y además un peróxido de hidrógeno, que es una especie que lo que queremos es ver si el mecanismo de cortar el ADN está involucrado en la oxidación, o sea, si es un corte oxidativo. Y podemos ver que los complejos 1 al 4 sí modificaron la conformación del ADN y que al añadir ese peróxido de hidrógeno se aumentó la actividad de nucleasa, lo que indica que los complejos inducen un mecanismo oxidativo para cortar el ADN. Sin embargo, este aumento en la actividad no fue tan notable para el níquel, para los complejos de níquel, y esto lo podemos ver aquí. Estos son de los complejos de níquel, entonces este que vemos aquí es la menor concentración de níquel y podemos ver ambas bandas. Entonces sí está cortando el ADN, pero no lo está cortando completamente, entonces no es tan efectivo como nucleasa. Y por eso también podemos concluir que quizás no sea tan bueno como antibacterial. También se vio que el corte oxidativo del ADN aumentó al aumentar la concentración del complejo. Finalmente, se hizo la técnica de microdilución para ver la actividad antibacterial de los complejos. En esta técnica, tú pones distintas concentraciones del antimicrobial y pones la bacteria a ver si hay crecimiento bacterial. Mides la concentración inhibitoria mínima y entonces con eso vas a poder ver cuán efectivo es como antibacterial. Mientras menor es el valor, pues mejor es como antimicrobial. Podemos ver que los ligandos tienen valores altos de M y C, entonces por sí solos no funcionan como antibacteriales, pero en los complejos 1 al 4 vemos una mejoría en este valor, especialmente para los complejos 1 y 2, que podemos ver valores tan bajos como 3.9 para bacterias gram positivas, pero sin embargo, para los complejos 3 y 4 los valores no son tan buenos como se puede desear. Tenemos también a ciprofloxacina, que es un antibiótico, para comparar, y como pueden ver son valores bastante bajitos. Con esto podemos ver que los complejos 1 y 2, que son los de cobre, fueron los mejores como antibacteriales y fueron más efectivos para las bacterias gram positivas. Entonces, esto también le da a entender al autor que el mecanismo de acción de estos complejos está involucrado con la pared celular de la bacteria, ya que la diferencia entre las bacterias gram positivos y gram negativos es la presencia o ausencia de una membrana externa. Entonces, una explicación para decir por qué es que los complejos muestran una mejor actividad antibacterial comparado a los ligandos por sí solos es que una disminución en la polaridad de metales, de iones metálicos, después de enlazarse al sistema NNS, aumenta la lipofilicidad de la molécula, lo que lleva a que pueda entrar fácilmente a la célula y pueda ejercer su mecanismo dentro de la célula. Y entonces mencioné ahorita que había una diferencia entre los dos ligandos con un grupo cloro para ver si había un efecto por la electrofilicidad del sustituyente, pero se encontró que no había ninguna tendencia clara. En conclusión, los complejos sintetizados pueden interactuar e inducir el rompimiento del ADN, lo que presenta un posible mecanismo antibacterial. Los complejos tuvieron actividades antibacteriales que eran dependientes de la concentración y entonces los complejos de cobre fueron los más efectivos, especialmente en contra de bacterias gram positivas. Esto va a concluir que estos complejos de cobre pudieran ser buenos precursores para drogas a ser usadas en contra de enfermedades patogénicas causadas por las bacterias gram positivas. Aquí están nuestras referencias y les agradecemos mucho por su atención.
All right, thank you guys. So if anyone has a question, please post it in the chat. I'm going to ask a few questions. All right, so one, I was just wondering, did they present any solution stability studies for the copper or nickel complexes for us to understand how stable and how intact these compounds would actually be, particularly at a physiological pH, physiological conditions?
Aparte de lo de la estabilidad termal, que nosotros encontramos que no era relevante, porque las temperaturas a las cuales se descomponían eran extremadamente altas, que no se comparan a las temperaturas del cuerpo, no recuerdo que hayan hecho ninguna comparación de estabilidad. Christopher, ¿tú? ¿Sí?
Bueno, no hicieron ningún estudio de especiación de lo que sería los complejos en soluciones acuosas con pH relevantes a lo que serían los pH fisiológicos. So, no, entiendo que no se hizo ningún estudio para evaluar eso.
So with that in mind, did they include some controls with just the metals, like for instance, any salt forms of the metals, just to make sure that what they're looking at was in fact a property of the complex?
Sí, déjame mostrarlo. Bueno, lo puedo explicar. Sí, y también tomaron las medidas de minimum inhibitory concentration de los nitratos de los metales, de cobre y de níquel, y parece que los valores eran bastante altos, y esto lo que entendimos que estaba mostrando era que los metales por sí solos no ejercían el efecto antibacterial, que necesitaban de los ligandos para poder tener el efecto.
Yeah, it could also be a situation of maybe not necessarily entering that well, or perhaps, you know, copper is something that's really important so that maybe just by the entry is not necessarily going to hurt these particular strains. Another question that I have is, there's more thinking outside the box. So if DNA is a target potentially of these compounds, what would make these compounds selective for bacteria and not hurt the host?
Pues la verdad yo considero que no, considerando eso, que un posible mecanismo de acción sería la interacción con el ADN, pues eso indicaría que no deberían ser tan selectivos para lo que sería la bacteria en comparación con lo que sería el host, que pues sería el organismo, el ser humano. Pero en el artículo ellos presentan también que una de las interacciones que también esta droga puede tener con la bacteria es con su pared. Y si este es el caso, pues entonces ya tenemos un mecanismo por el cual es más selectivo, porque pues las células eucariotas del ser humano no poseen pared. So ya ahí tendríamos entonces un mecanismo alterno que sería más selectivo para lo que sería la bacteria.
Right, exactly, because that was one of the points about the development of antibacterial compounds, is to try to target those things that distinguish bacterial cells from human cells. And so something like that would be interesting to explore. Okay, well, thank you guys. All right, so our next presenters.
Somos.
Yeah, I think Daniela has to stop. Yeah, there we go.
Yeah.
Okay, you have you have 2 minutes remaining, I'll let you know.
Okay, thank you. Well, good afternoon. Today, Glorimar Miranda and I, Lisby Santiago, will be presenting the research article titled Synthesis, Characterization, and Evaluation of Antibacterial, Antiparasitic, and Anticancer Activities of Aluminum-doped zinc oxide nanoparticles. So first, I'm going to be covering some basic background key points for a better understanding of the article. So I'm going to start with metal oxides and nanomaterials. So the basic structure of a metal oxide is a cationic metal sensor bound to oxygen ligands. These basic structures can further coordinate into broader arrangements depending on the metal center. So in the past decades, researchers have developed different approaches for the synthesis of metal oxides, resulting in a range of nanomaterials with different applications. Nanoparticles, nanowires, and nanotubes are examples of recent nanomaterials that have been developed. So these nanomaterials have a diversity of applications, including chemical sensors, batteries, environmental remediation, catalysis, and many biomedical applications. So metal oxide nanoparticles range in sizes from 1 to 100 nanometers, and the nanoparticles' unique and advantageous properties are largely due to their reduced size. So these nanomaterials can have a large percentage of atoms in their surface, which permits having a high surface area, greater reactivity, and enhanced chemical properties. Their size also allows for their application in fields like nanomedicine and nanotechnology. So for example, they can easily be made to interact with biomolecules, and some can even undergo intracellular delivery. Zinc oxide nanoparticles will be at the focus of our presentation, since in this article the researchers work with these type of nanoparticles. So zinc oxide nanoparticles are naturally occurring in minerals and they are listed as a safe substance by the Food and Drug Administration. Studies have shown that zinc oxide nanoparticles are non-toxic to human cells, and they also hold great biocompatibility. So here I present the three crystal structures that zinc oxide nanoparticles can form, which are rock salt, zinc blende, and wurtzite, being wurtzite the most thermodynamically stable. Previous studies have shown that zinc oxide nanoparticles hold antibacterial and anticancer activity, but the exact mechanism of toxicity is still under debate. What is of general consensus is that zinc oxide nanoparticles can exert their toxicity by causing damage in the outer membrane of bacteria and producing reactive oxygen species. So in this image, I present three examples of the most common mechanisms proposed. The first one is by damage through electrostatic interactions. So Sang and coworkers suggested that there are strong electrostatic interactions between the nanoparticles and the bacterial cell that damage the cell membrane. So here they suggest that the zinc oxide nanoparticles are positively charged when they are suspended in water, and thus they can interact with the negatively charged bacterial surface, which then leads to the membrane disruption. The second mechanism is through the release of zinc ions. So Casemets and co-workers propose that toxicity of zinc oxide nanoparticles is directly proportional to the solubility of zinc ions in the medium. Zinc ions have been shown to negatively impact active transport enzyme systems and can interact with other species, causing disruption of the cellular environment. However, this proposed mechanism is limited in that the dissolution of zinc ions from zinc oxide is dependent on many variables such as pH, particle size, other components of the medium, exposure, time, among others. And another known property of zinc oxide nanoparticles is that they're inclined to produce reactive oxygen species that can cause cellular damage. Researchers believe that this mechanism was due to the semiconductor properties of the zinc oxide. So, for example, Ragopath and co-workers showed that there was an increase in reactive oxygen species production from the nanoparticles when they were exposed to UV and visible light. And it was believed that there was a correlation between the UV and visible energy absorption, photon reaction, and the release of reactive oxygen species. These ROS are, for example, superoxide anions, hydrogen peroxide, hydroxide, and they can participate in the destruction of cellular essential macromolecules. ROS can also oxidize proteins and lipids, which can damage the cell membrane, impact permeability, and inhibit essential metabolic processes. However, alternative studies have shown that ROS activity can occur in the dark, so further studies are needed to better understand the cause behind this potential mechanism. And I wanted to also say that trying to elucidate what mechanism is causing cellular distress when talking about zinc oxide nanoparticles is very complicated because of the many variables these nanoparticles have. Also, I think it's important to note that the mechanisms I present are not necessarily exclusive. That is, we can observe the release of zinc ions and a consequent production of ROS, both of which would cause cellular toxicity. So the chemical, mechanical, and morphological properties of nanoparticles are directly dependent on the way they are synthesized. So it is very important to take note of the synthetic approach of the nanoparticles to understand their properties and potential applications. In this study, the researchers worked with laser ablation in liquid technique. Here I illustrate a general structure of the laser ablation system for the synthesis of nanoparticles. Generally speaking, laser ablation is a process in where material is removed from a solid by irradiating the solid with a laser beam. In this technique, a laser beam is directed through a focusing lens and into a solid surface that is suspended in a liquid environment. The interaction of the laser beam with the solid target removes part of the solid surface, resulting in a suspension and the formation of the desired nanomaterial. In the present study, the solid surface was a zinc metal target, and the laser beam was pulsed with enough energy to release the zinc particles into the aqueous environment. This ablation of zinc reacts with water molecules to then produce the zinc oxide nanoparticles. And in addition of the synthesis of these nanoparticles using laser ablation, the researchers also wanted to dope the nanoparticles with a material that could potentially enhance the activity. So aluminum was chosen for its availability and low toxicity. The doping of the nanoparticles was also achieved using the same technique by replacing the zinc target with an aluminum surface after 100 pulses of ablation. The synthesis of nanoparticles here via laser ablation in liquid is presented as a simple, fast, efficient, and environmentally greener alternative for the synthesis of nanoparticles. The objectives of this study were the synthesis of zinc oxide nanoparticles as well as aluminum doped zinc oxide nanoparticles using the laser ablation in liquid technique, the characterization of the nanoparticles, and the evaluation of activity. Initially, the synthesis and doping with aluminum were carried out using the liquid ablation technique, as I previously mentioned. Then the resulting nanoparticles were characterized using X-ray diffraction, UVB spectroscopy, field emission scanning electron microscopy, and energy dispersive spectrum analysis. Finally, the activity evaluation of the nanoparticles was done to review their potential as antibacterial, antiparasitic, and anticancer. The laser system was used with a neodymium-doped yttrium aluminum garnet, providing pulses of 1064 nanometers, and the reaction was performed at room temperature, assembled as I illustrate here in the figure. The laser beam was concentrated towards the zinc target with a different number of pulses. Once the beam interacted with the zinc surface, ablation of the material was achieved, and the nanoparticles were acquired as a suspension. And finally, after 100 pulses, the zinc surface was replaced to an aluminum surface so that zinc oxide nanoparticles could be doped.
So once they synthesize the nanoparticles, they determine the mass concentration that they managed to obtain suspended in the solution. As you can see here, there is a sample code. This is very important for the future analysis, although I will be identifying the important ones. So they have a control, and from A to F, they synthesize regular zinc oxide nanoparticles without the doping and obtain escalating mass concentrations. And from G to J, they doped zinc oxide nanoparticles that had 100 pulses to obtain also escalating doping ratios. Here, it's the graph representations, meaning that representing that there's a linear relationship with the number of pulses and the mass concentration of the zinc oxide nanoparticles, and also there's a linear representation with the number of pulses with the doping ratio. The XRD analysis of the undoped zinc oxide nanoparticles show an hexagonal word site structure that they associate the signal in the 43.76 degree with the 101 plane that they associate with the zinc 2 plus ion. Also, the XRD of the aluminum doped zinc oxide nanoparticles represent a hexagonal structure, and they associate the synthesis of the doped nanoparticles with the peak in the 43.79 degrees with the 320 plane. With the UVV spectra of both the zinc oxide nanoparticles and the doped zinc oxide nanoparticles, they determined that with each of the nanoparticles, there's a peak that centers in 260, both with the undoped and the doped nanoparticles. And in particular with the non-doped nanoparticles, we exhibit the behavior which increasing the number of pulses, there's also an increase in the absorbance. This is also can be related to the amount of concentration that is generated with the increasing amount of pulses, which results in an increase in signal. However, in the doped zinc nanoparticle UVs, we observe this trend, but only when we compare the 0.2% and the 0.27% with each other, and with the 0.33 and the 0.42%. They conclude a possible theory in which the lower percentage of the dope ratio is present, has a higher percent of absorbance. This they associate with the possible scattering of the nanoparticles, and also possibly the aluminum reflectance that causes the higher percentage to appear at a lower absorbance. They used SEM and EDS. The EDS they used mainly to determine the purity of their nanoparticles, to determine with the zinc oxide nanoparticles that there's only zinc and oxygen present, and with the zinc oxide doped nanoparticles to determine that there's only zinc, oxygen, and aluminum. So with the SAM, they managed to observe a great variety of shapes and also average diameters. For example, with the 25 laser pulses of the zinc oxide nanoparticles, they obtain nanoplates and flakes with an average diameter of 44, while with 50 pulses, they obtain hexagonal rod shapes. With 75, they obtain spherical shapes with average diameter of 24 to 42. And with 100 pulses, they obtain both spherical and flakes shapes with average diameter of 34 and 69. With 125, they obtain nanowires with an average diameter of 30, but they also observed spheres that have a high agglomerate behavior with 22 and 31 as average diameters. In the aluminum doped zinc oxide nanoparticles, the 0.2% they determined to be nanowire shaped with an average diameter of 16 to 27. The 0.27% they determined to have an hexagonal nanorod shape with an average diameter of 126. And the 0.33 also have a nanowire shape with 18 to 22 diameter. And the 0.42% they obtain spherical shaped particles with 22 to 32 average diameters. And with the antibacterial data analysis, basically to determine the optical bacteria density, they suspend bacteria in saline solution and they take 0.9 milliliters and they move it to a cell, and to that they add 0.1 milliliter for a total of 1 milliliter solution of nanoparticles, and they incubate that for 3 hours. Then they use UV at 60 nanometers to determine the optical density. So in a matter of how much the nanoparticles work as inhibition for for bacterial growth, they obtain lower optical density. So in the graph form of the inhibition rate, they determine with E. coli that there's an increase of inhibition rate as they move up the zinc oxide nanoparticles that are not doped. But once they reach the 100 pulse mark, they obtain a decrease and continue decreasing with the 125 pulse nanoparticles. And once they begin with the doped nanoparticles, which is G, corresponding to 0.2%, they continue having a decrease in inhibition rate, and then as they move up the doping percentage, they obtain higher inhibition rate to obtain a max of 68.66% with the 0.42% ratio of the doped nanoparticles. And with the they also tested the S-Iris for their antibacterial effect. Using the same method, they obtained their optical density to determine the inhibition rate, which which they determined to have a relatively more stable working high with the inhibition rate. So once they move up with the pulses, they obtain better inhibition, and to reach a max of 66% inhibition with the max doped nanoparticles.
Okay, there's 2 minutes remaining.
Okay. So they also determined the inhibition rate of the antibacterial to determine the same type of trend as the previous analysis. They also did with the antiparasitic activity. They basically took a culture and determined the growth inhibition to determine also a escalating trend with the max nanoparticles, the doped nanoparticles with the max inhibition rate. And they also, with the morphological assay, they determined the same. The zinc oxide nanoparticles have an inhibition rate and produce less viable cells for the parasitic. You observe the same trend with both of the types of parasites that they use to evaluate. And with the anti-cancer activity, they use the same method as the antiparasitic activity to determine the same relationship where you obtain an escalated effect, with the maximum inhibition being from the 0.42% doped zinc oxide nanoparticles. In this case, the morphological assay observed indicated morphological alteration with cell shape and also clumping and a disturbance in cell communication. In conclusion,
Zinc oxide and aluminum zinc oxide nanoparticles were both successfully synthesized using the laser ablation technique. Characterization showed an hexagonal structure and high absorption in the UV region, and aluminum doped zinc oxide nanoparticles, as well as the zinc oxide nanoparticles, proved to have antibacterial, antiparasitic, and anti-cancer potential.
All right, thank you. So I want to ask you guys, so what do you think exactly is the reason for that potentially higher activity with the group J, so that particular version of the material?
I think it's mainly due to the morphological type of affection that the doping does to the nanoparticles. They also mentioned that with the doping, it actually kind of affects the size. So I believe that facilitates the functionality of the nanoparticles.
Well, how big were those nanoparticles?
They were spheres from 22 to 32 nanometers.
Okay.
Mm-hmm.
And what exactly? Yeah, go ahead.
No. They're relatively small, but when you look at some of them, they tend to be slightly larger. So you have 30, you have 126, and also the shape, which the J are spheres specifically.
All right, because that's a question that Javier had about what seems to be an optimal nanoparticle shape. What exactly is the aluminum doing?
En el artículo brevemente mencionan que ellos piensan que el aluminio permite mayor producción de las especies reactivas de oxígeno porque la banda de conducción de aluminio permite que haya un mejor catálisis y entonces mayor producción de estas especies reactivas.
Right. So in this context, are we looking at activity that is UV activated?
Yo mencioné en la introducción que las nanopartículas de óxido de zinc se han visto que son activas por UV y por energía visible, pero también se ha visto esta actividad en ausencia de energía UV visible. Así que todavía no se conoce bien realmente si realmente esta energía es un catalizador, pero es una hipótesis.
Okay, so perhaps the aluminum is influencing some of the semiconductor properties there. Okay, that's interesting. I was just kind of curious about what's actually facilitating that. If it's believed to be some sort of Ross generation, how is actually influenced that, and what would be the source of energy? Okay, so that's it, guys. So we move on to our next presentation. Okay, Andrea, so I'll let you guys know when you have 2 minutes remaining.
Yeah, sorry about that. I forgot to turn on my microphone.
That's okay.
All right.
Andrea, is there a delay?
I'm not sure. Omar, do you have your?
¿Qué pasó?
Okay. Yeah. Okay.
You guys ready? Okay, good.
Ok, pues buenos días a todos. Andrea y yo le estaremos hablando de compuestos a base de manganeso para actividad antiparasítica y antibacterial. I'm going to switch to English now to practice a little bit. So, Andrea, could you switch to the next slide? So, I'll give you a little background on what we're doing, on what the authors did. I'll try to not be cut down a little bit because it's a bit redundant. A lot of information we've already talked about in class. So next slide. So basically an approach that, as most of you know by now, is gathering a lot of attention is using in inorganic medicinal chemistry, is using already established drugs as ligands for metal complexes. For example, as we learned last Tuesday in class, chloroquine is an antimalarial drug that has been very successful, and a ferroquine counterpart, also an iron-bound chloroquine, basically, has also found itself to be very successful in clinical trials, even against malarial strains that are resistant to chloroquine. So this has inspired a lot of research based on exploiting the chloroquine drug. Ruthenium and gold complexes have been studied as well, and they have shown high antimalarial activity. So the authors of this paper have explored other non-chloroquine ligands as potential drug candidates, specifically rhodium and iridium and heterocyclic carbene complexes that you can see in the bottom left. The M is can be rhodium or iridium. In the paper, they found that it didn't really matter which of the two metals they used. Anyway, the point is that they explored. No, Andrea. Okay, they explored the carbene complexes as well as cimentrine chloroquine conjugates, which is the bottom right, to see if they had any promising antiparasitic activity on Trypanosoma brucei, and they found some activity, but the major problem was that there was poor selectivity in terms that they were also toxic on mammalian cell lines. So the authors in this paper revisited the manganese tricarbonyl moiety seen here in cimentrine and the bottom right. I was trying to use my mouse as a pointer. So they want to revisit the manganese moiety in the context of azole antifungal drugs. So next slide. So the authors synthesized a series of compounds basically based on the interaction of the imidazole group in the azole drugs. I will show you them in a minute. Imidazole is an intermediate Lewis base, which interacts with the manganese tricarbonyl moiety, which acts as an intermediate acid. So the authors suggest that these compounds are very stable, and they want to basically explore, and they want to do a series of assays and compare if the non-methylated version is actually less active than the methylated version. So next slide. So the azole-based drugs that they want to explore are all very established and known drugs. They're all commercially available. Usually they come in the form of creams, ointments. Clotrimazole and miconazole are on the World Health Organization list of essential medicines. Ketoconazole has had more than 2 million prescriptions in the 2017 in the US, so they are very well known and studied. And so the fact that they're all azoles, specifically imidazoles, they contain the imidazole group. You can, I mean, if you could circle it in each of the 3 drugs. So basically, they have the same mechanism, which we will see in a minute. And the next slide. So I made this little figure to like summarize the. Oh yes, my bad. To summarize the process overall. So in general, fungi, there's an enzyme called lanosterol 14 alpha demethylase that converts lanosterol into, through a series of steps, into the sterol ergosterol. Ergosterol is necessary for cellular membrane health. It moderates permeability, nutritional transport, and chitin production. So many antifungal drugs have explored this as a potential target. The drugs in mind have all been known to basically work by inhibiting the lanosterol 14 alpha demethylase. So this enzyme is part of the family of cytochrome P450. This family of proteins contain an iron-bound heme center. So it is thought that the imidazole, the free nitrogen in the imidazole binds to this iron, bounds to the iron heme center. So this effectively inhibits the lanosterol. And since it's inhibited, it produces less ergosterol, and thus the cellular membrane of the fungi has increased cell permeability, which eventually leads to cell lysis. So the authors have found that in some parasites, this ergosterol dependence is actually very similar as well. They expect that inhibiting lanosterol 14 demethylase can actually lead to parasitic death in many cases. So I'll now leave you with Andrea to speak a little more about the synthesis and characterization process of these compounds.
So the aim of the researchers was to explore the impact of azole drug coordination to stable manganese tricarbonyl complexes. And so they did so first by synthesizing their compounds of interest. They treated the manganese tricarbonyl complexes that were either 1 or 2, as seen on the table. They would substitute the bromide, and then afterwards would do the addition of the azole ligand. They followed this by column chromatography, and they stated that the end result, the complex, seemed air and moisture stable. And they also obtained relatively moderate to good yields in their synthesis. They characterized the complexes via infrared spectrometry. They identified the characteristic 3-carbonyl stretching bands. And they also used HNMR and CNMR, and they indicate that they did observe the symmetrical bipyridine coordination. Moreover, they used XRD to analyze CTZ, and they identified that the manganese atom is in a pseudo-octahedral environment where the moiety is coordinated by the bidentate bipyridine ligand in a symmetrical way, and that the azole ligand was bound by the imidazole N1 atom. They conducted their biological activity studies in a fashion that's very similar to what my peer Daniela explained. They used serial dilution to do so. And they used both gram-positive and gram-negative bacteria. When it comes to the gram-negative bacteria, they did not observe any significant effect in inhibiting the growth of bacteria. So what they were calculating was the MIC, the minimum inhibitory concentration. And as you can see, these numbers are all in micromolar, and they are almost all above 40 micromolar, which is not something that you would want to use potentially on a living system. But the story is very different when we look at the gram-positive bacteria. And that is because they almost all showed significantly lower MIC values, notably with compound number 7 that has
Andrea, I'm not hearing you. I'm not sure if you're having a mic issue. Okay, let's try to figure this out. Omar, are you there?
Yeah, I'm texting Andrea to see what happened.
Do you think you can cover for her?
Not really. I mean, I can, but I think. Give me a minute.
Yeah, just have her call into the.
Yeah, I'm trying to contact her. Se le fue la luz. Pero
Yeah,
acaba
I'm
de
gonna
volver.
project for you guys. Have her call into the meeting, okay?
Okay.
Hi, sorry about that. Can you guys hear me?
Yeah, I can hear you. I'm gonna project for you, okay? Or you're gonna try to share it?
Oh no, I can project. It's just that I lost the electricity for a second.
Okay.
Here we are. All right. Where did I last?
Yeah, you were at the
log?
gram-positive, and that there was an improvement over the gram-negative.
Okay, thank you. Okay, so essentially, they did see a significant difference in the inhibitory concentration for the gram-positive bacteria. And as you can see, the compound 7, which has CTZ as its ligand, showed 0.625 micromolar as its minimum inhibitory concentration, which is great because it's sub-micromolar. It's very low amounts that inhibited the growth of the bacteria. They also noticed that the metal complexes, generally, save for a few outliers, resulted in more inhibition than just the organic compound alone. Among the metal complexes specifically, the relationship was as such. The least effective was KTZ, followed by MCZ, and the most effective one was CTZ. They noticed a general trend where if there was where the activity was increased in relation to a decrease in molecular weight. And they compared these findings to findings that they had with other compounds that they had studied. that were rhodium and iridium complexes, and they saw that these were more effective than the ones that they had obtained. The lowest number that they obtained was 2.5. In this case, they obtained 0.625. And so that begs the question, why is there such a discrepancy between the gram-positive and gram-negative bacteria? And so as some of my peers have mentioned, gram-negative bacteria tend to be able to change the hydrophobic properties and other factors in their membrane, which can result in resistance, whereas gram-positive bacteria lack the layer to do so. And so many antibiotics, such as vancomycin, which, like beta-lactam antibiotics, they target the wall peptidoglycan. They're ineffective against gram-negative bacteria because they have the chemical properties that allow them to adapt to that type of situation. And so this and the structural relationship that they proposed could possibly explain why these compounds were ineffective against gram-negative, but they do so against gram-positive.
Okay, so now I'll be talking about the antiparasitic studies that they did. They basically tested. Andrea, siento como escucho un feedback. No sé si puedes apagar.
Okay.
Okay. So they tested on the Leishmania major and Trypanosoma brucei. They did proximal slide, please. They did they measured their activity by IC50, and they measured the how selective the compounds were by calculating the selectivity index. So they did this by dividing the IC50 value of two different mammalian cell lines over the IC50 value of the parasitic IC50 of the parasite. So first, for the L major, they found that the metal complexes, which are in the third column, the metal complexes all did much better than they were more potent by a magnitude of 1 than their non-metallated versions, which is good, except for the fact that when they calculated the selectivity index, the selectivity indexes were considerably low, meaning that they were also damaging the mammalian cell lines. So based on these results, the authors established that these compounds are not suitable for anti-leishmanial chemotherapy, at least as they are. So for the Trypanosoma brucei, they found different results. They were also, the non-metallated were also less potent than the metallated compounds. Most of them also had issues with the selectivity, for the exception of the first compound, which is ketoconazole without the methyl ester substitution. This one actually had the highest selectivity index in both mammalian cell lines, indicating that it has a considerably higher selectivity. So basically, the authors established that this compound is the most promising one, and that it should be studied and beyond, since they really didn't do. They mentioned that these compounds are very stable, but they did not present really any kind of speciation study or mechanism studies. They expect that these compounds work solely on the function of the drug, of the original drug. So more studies really need to be done regarding how the metal affects this process, if it remains the same, or how is the metal really enhancing the original drug, which is an effect that is observable in all cases, even when there is poor selectivity. But to summarize, overall, the most compounds were more active with the metal complexes. There was a lot of poor selectivity, except for one of the compounds. Something I forgot to mention is that most compounds, actually, comparing the metallated compounds, most that did not have the methyl ester substitution actually did better than the methyl ester substituted. And overall, that'll be it. If you guys have any questions, let us know. It was a very short paper.
All right, thank you guys. So yeah, we are going overtime. So I'm going to ask you questions. I will appreciate if people can stay. If others can't, that's fine. All right. So I do have a question. So I see that in the parasite work, which is what you were presenting, Omar, there was some insight into testing a mammalian cell line just to get some general toxicity information. Obviously, one cell line is not enough, but using that information and then going back to Andrea's presentation of the effect on the gram-positive bacteria, could you really say that that compound 7 is as great as it seems?
I don't really think so, because I think the whole selectivity problem is significant. At least in the parasitic work, it definitely had enhanced activity in comparison to the non-metallated ones, but it also had really poor selectivity. Actually, I'm looking at the table now, it had one of the worst selectivity indexes.
Right, so that's why I was kind of curious, because yeah, maybe for the parasitic work, if it was higher concentrations, it's a different story. But we're looking at an effect which is 1.25 micromolar for the IC50, and that's about the concentration range, if I'm not mistaken, because I didn't see an actual concentration unit in the bacteria stuff. We're at that same level for the MIC values, so I'm not sure it would be that promising. I mean, in general, these are just some attempts to get some insight as to these type of compounds. Another question that I have for you, and I see Gladys Maris is getting into it, is why the smallest ligand has a major effect. So I have that similar type of question, which is they chose these azole ligands, right? But the sort of backbone or the substituents are quite different. So that makes it a little bit, for at least in my opinion, a little bit hard to do some SAR type characterizations. But nonetheless, why did they choose those ligands? And why do you think the smallest ones, as Gladys Maris was asking, might have been more effective?
So I've been asking myself that as well, because the authors don't really elucidate much on the structural aspects and possible mechanisms. I do think that perhaps they have on the other papers worked on similar compounds, and in one of the papers they found that compounds that had bulkier substituents actually performed better, though I don't think that trend is really visible in this paper. So I assume that I'm not truly sure why that works. We will have to examine how the metal drug complex works, how it enters the cell, and how it functions on if it even has the same mechanism, if it works on the cytochrome P450. The authors argued that the complex is very stable and it might actually stay intact inside of the cell, though they don't really have any speciation data to back that up. So I am not really sure how to answer that.
Yeah, I've been trying to wrap my head around that since we started reading the paper, because actually in the introduction they mentioned that it's really important that you have the speciation studies to understand the stability of the compounds, but they themselves don't present that data, for starters, and secondly, they also don't present a possible idea as to how the drugs are, one, entering, and two, what is their mode of action. I do believe that it's possible that because it's a smaller, it does have an easier time going through the barrier of the bacteria and then, entering the cell and whatever method it uses, doing so by that. But they don't really present any even idea as to how it's working.
Yeah, I think we really have to. I felt like this was like a somewhat preliminary study to like settle out the best candidates for those studies, because I think it's really important to establish how this drug complex like actually works in like terms of like entering the cell and how it works with the targets, which is information that we really don't have in this paper, at least.
Okay, and so the very last question is Jemily's question. She notes that the metal compounds seem to be more active relative to just the organic compounds or the free ligands, right? Except for complex 4. Any insight about that?
Well, based on the trend that the less bulky substituents did better, I think this is actually similar, because compound 4 is ketoconazole, which has the highest molar mass of the 3 compounds, and 4 also has the methyl ester substitution. So just me thinking out here, I think maybe that has to do a little bit with its bulkier aspect. Could perhaps be making it a little bit more difficult to be delivered into cells, or just simply not like interrupting its mechanism.
Okay. All right. Well, thank you very much. And thanks to the class for being able to stay a little bit longer. All right, everyone. Well, enjoy your weekend.